In this lecture, we're going to introduce the next extension of the correlation coefficient, and that's regression analysis. And the main statistic used in regression analysis is what's called the coefficient of determination. And this statistic assesses the degree in which the variability in one variable can be determined from the variability in the other variable. And this coefficient of determination is based upon the Pearson product moment correlation coefficient of R, sometimes expressed as R subscript xy for the relationship between x and y. And this value is just simply determined by multiplying the R value by itself, or the R value squared. That statistic is the coefficient of determination, and it represents the explained or common variance of the relationship between two variables. It's also referred to as the effect size of a relationship between two variables. And just a few points to note here: that raw scores will deviate vertically on the scatter plot from the regression line, and deviating vertically assumes that number is taken at a fixed x value. But the big question with the coefficient of determination and regression analysis is to try to quantify how much that vertical deviation occurs. And so what we ask here is, how much can the x variable explain the degree of variation away from the regression line of the criterion or dependent variable. And the linear regression equation that is generated from a regression analysis is y hat equals a plus b x, where y hat is the predicted y value, and that's the value along the line of best fit and not the y value in the original set of data. X is the value that we could put into the equation in order to predict the outcome along the y-axis. A is a coefficient that is the y-intercept, in other words, the value of y when x equals 0, and b is the slope of the regression line that we'll focus on here in a moment. And so this equation is the equation of a straight line and is the so-called regression equation. And the coefficients that become important elements that characterizes the relationship between two variables are given by b and a. And b is the slope, which is a measure of the rate of change of the y variable as a function of the x variable. And the slope can be positive or negative, and it's the slope that accounts for the direct or inverse relationship between two variables. The a coefficient, or the a value, is the y-intercept. In other words, it's the value of y when the regression line hits the y-axis, and that occurs when the value of x equals 0. And so if we take a look at the various elements in these equations, R is the Pearson product moment correlation coefficient value that we see entered into calculating the slope, and it's entered into calculating the y-intercept. And if you notice these other variables, these other elements of these equations, these are all elements that were first determined from descriptive statistics. And so when we have a set of data, it's why it's always important to first calculate the mean and standard deviation if those variables are ratio or interval type, where SY is the standard deviation of the criterion or dependent variable, SX is the standard deviation of the predictor or independent variable, Y bar is the average score or the mean of the y variable, and x bar is the mean or the average value of the x variable. And in this example, we examine the relationship between blood pressure and age in years. And so we see that this relationship through this analysis is best described as a straight line and is a direct or positive correlation between these two variables, indicating that blood pressure is positively correlated with age. And what we see here on the scatter plot, once again, we have the raw score from one participant of a certain age. And very important here is y subtract y hat. And that difference between this value here, the observed value for this research participant, exists at a particular vertical distance from the line of best fit. And that is the residual. And the residual measures the magnitude of the error in the prediction. So the difference between the actual score and the score predicted by the line of best fit. And so once again, y hat is the predicted value along the line of best fit. So for this data point here, we would enter in this particular person's age into the prediction equation and calculate through to get a value that would be right on the line. But we notice that the actual value is greater than what is predicted for this one person, where y is the raw score, which is the actual observed value. And the expression of the residuals, so we see that each research participant deviates by a different amount from that line of best fit, and the SEE is referred to as the standard error of the estimate, and the standard error of the estimate is analogous to the standard deviation for descriptive statistics, and is a one number that provides us with an indication of how far we can expect the prediction to vary from the actual value. And we see here that the standard error of the estimate incorporates the standard deviation that was obtained from the descriptive statistics, a standard deviation of y, and the other variable that's included in this equation is the coefficient of determination, which is the correlation coefficient squared. So this ends this lecture in our unit here on correlational research.